Hello, this is Gregory, and today this lesson will be on operations on functions. Operations on functions. And we are going to talk about addition of functions, subtraction of functions, multiplication and division of functions, and an operation that's specifically designed for functions, that is composition of functions. So we're doing four arithmetic operations on functions and an algebraic operation, which is an operation that is designed particularly for functions. The PowerPoint slides that I will be using for this lesson are largely from Shauna Hader, who created them. She's a professor at Salt Lake Community College, and of course, again, I appreciate her preparing these PowerPoint lessons to make it easier for us. Let's get started. So, as a quick review of previous lessons, you remember that there are some domain restrictions that we've studied before. In particular, two particular domain restrictions are that when you have a variable in the denominator, you must make sure that the denominator does not equal 0. Any variable that causes the denominator to equal 0 has to be removed from the domain. And likewise, any domain variable, that is the independent variable, that is under a radical that causes under this radical an even index radical. That means a square root or a fourth root or a 10th root or a 20th root, any even radical. If you want a real number output, the variable that you use cannot cause the part under the radical, the radicand, to be negative. It has to be non-negative. So in short, if you have a fraction or a rational expression, you have to remove all values of the variable that causes the denominator to be 0. And if you have a radical expression, you have to remove all values of the variable that causes the radicand to be negative if the radical is an even index radical. Odd radicals like cube root or fifth root or seventh roots do not have that restriction. If there are no domain restrictions, then the domain is all real numbers. Later on in another lesson, we'll talk about another domain restriction which occurs from logarithmic functions. Now, let's get into the operations of functions. The first operation we want to talk about is the operation of addition, sum, f plus g of x. F plus g of x is just shorthand, very simple shorthand, for the addition of f of x plus g of x. Let's take a quick look at an example here. So let's say f of x is 2x squared plus 3 and g of x is 4x cubed plus 1. Then f plus g of x is simply f of x plus g of x. So we're going to write the expression for f of x, 2x squared plus 1, plus the expression for g of x, 4x cubed plus 1. And we will add and combine like terms. There are no other cube terms, so it's just 4x cubed, nor the x squared term, so that's just 2x squared, and then 3 plus 1 would be 4. So the result would be 4x cubed plus 2x squared plus 4. That all we did was add the corresponding parts of the expressions. Subtraction is similar, but just remember, when you're subtracting, we're subtracting the whole function. So f minus g of x is f of x minus g of x. So if we use the same two examples, we do f of x minus g of x, we're doing f of x minus the whole quantity of the function g of x. So we have 2x squared plus 3 minus, in parentheses, 4x cubed plus 1. Those parentheses are very important because we're saying we're subtracting the whole expression. Then I can distribute the negative to each term and both signs change. And then from there I can combine like terms, write it in standard form in this case, negative 4x cubed plus 2x squared, and then 3 minus 1 is 2. So remember now, when we're doing a subtraction, you must distribute the negative as appropriate. You're subtracting the whole function. Now, for a product, we are multiplying f of x multiplied by g of x. So when we look at our two examples again, we'll put both functions in parentheses, then we will distribute the parentheses. That's how we multiply polynomials. Each term in one pair of parentheses multiplied by each term in the other pair. So the 2x squared times 4x cubed is 8x to the 5. The 2x squared times 1 is 2x squared. The 3 times 4x cubed is 12x cubed. And the 3 times 1 is a 3. And of course, if we were to put this in standard form, we would put the 12x cubed before the 2x squared. But this is the result. in this case, we FOILed first, outer, inner, last, or really more precisely, distribute each thing in one pair of parentheses by each thing in the other pair of parentheses, and that gives us our final expression. Now for division, it's pretty straightforward again. F of x divided by g of x. We simply divide one function by the other. In this case, 2x squared plus 3 over or divided by 4x cubed plus 1. We cannot cancel when there's a division unless everything in the numerator is multiplied and everything in the denominator is multiplied. In other words, we will have to factor first if possible. Now in this case, it doesn't factor very neatly. The top doesn't factor to be real number coefficients, and the bottom gives some really weird results. So we leave it like that. So this expression cannot be simplified anymore. We leave it as it is, and that is the result. A couple of things more before we do some examples. When you're talking about the domain of a combination of functions, you have to make sure that you follow the same rules as domain, but remember that whatever works in the combination must work in each function. So in short, when we're trying to find the domain of a sum, difference, product, or quotient of functions, here are the guidelines. First of all, I'm going to use a little notation here. Domain subscript f means the domain of f, and range subscript f just means the range of f. The domain of f plus g is simply where the two domains intersect. We look for the domain of f, we look for the domain of g, and see what they have in common. We can only use, as in the combination, what the domains have in common. The same applies if we're doing subtraction, and the same applies if we're doing multiplication. We can only find the domain of a multiplication, an addition, or a subtraction of functions if we look for where those two regions overlap, where they intersect, what the domains have in common. A similar thing occurs when we do division. The domain of a division must only occurs where the two domains intersect, but there's an additional restriction. We have to remove whatever causes the denominator function, the function that we're dividing by, the dividend, to be equal to 0. So in this case, we take the intersection and we subtract any additional function domain that will cause the denominator to be equal to 0. So let's do a few quick examples here. All right, let's talk a bit about these examples. Now, in this question here, for a number, we have the two functions that are listed here are f of x and g of x, and the graphs are indicated. We're going to answer questions number 83 to 90 related to these two graphs. The graph of f of x is the blue graph, and the graph of g of x is the burgundy or red graph. So let's take a look at what they're saying here. F plus g of -3. What we really mean is we want to find f of -3 plus g of -3. So we're going to go to the function, we look for -3, the corresponding y value for the f function is -3 and the corresponding value is 4. So the point is -3, 4. So f of -3 is 4. G of -3 is 1 because the point that corresponds to that is -3, 1. G is the red graph. So we're adding 4 plus 1. So f plus g of -3 is 5. Now I'd like you to try the others on your own before you check what I do with my examples. Now you can pause the video, of course, and look at how I did these. Now we do g of f of -2, which really means we're doing g of -2 minus f of -2. Now if we look at the graph here, g of -2 is 2, and f of -2 is 3. So we're doing 2 minus 3, which is -1. F of g of 2 really means f of 2 multiplied by g of 2. So f of 2 is that's the blue function, that's -1. And g of 2, that's the red function, is positive 1. So negative 1 times positive 1 is just negative 1. Now g over f of 3 is the same as g of 3 divided by f of 3. So g of 3, we look for g of 3, 1, 2, 3. G of 3 is 0. And f of 3 is, let's see here, negative 3. So we're dividing 0 by negative 3. Of course, 0 divided by any other number is 0. So g over f of 3 is 0. Now let's say find the domain of f plus g and find the domain of f over g, and then graph the functions. Now the domain of f plus g is equal to the domain of f intersecting with the domain of g. Now the domain of f, is from negative 4, up to positive 3. So it's negative 4 to positive 3. We're going to see where that intersects with the domain of g, which starts at negative 5 and stops at positive 5. As you can see, the two functions start intersecting at negative 4 and stop intersecting at 3. So that's the overall domain of the combination. So when we're doing a combination of the two functions, we can only do from negative 4 to 3. Now, for the domain of f over g, we again do the intersection. Domain of f divided by g is equal to the domain of f intersect with the domain of g, but we also have to subtract whatever causes g of x, whatever value of x causes g to be 0. So we're going to find out what values of x cause the denominator to be 0, and we're going to remove that from the intersection. So first we will determine what the intersection of the two domain regions are, which we just did, and then we will find out what values of x causes the denominator to be equal to 0. So we're talking about intersection from negative 4 to 3, because we just did it over there, minus, let's see what values of x cause the denominator function to be 0. We have to take out negative 4, and we have to take out positive 3. So we have to take out negative 4, and we have to take out positive 3, which means the domain is now only from negative 4 to 3, parentheses. That means the endpoints were taken out of that overlapped region. So now it's an open interval. So negative 4 and negative 3 won't work in f over g of x, because negative 4 and negative 3, when they're input into the function in the denominator g of x, that gives you no solution. Now, the next part is to graph f plus g and f minus g. So let's see if we can get through some of that one right now. F plus g and f minus g. So what we do first is we will list out our key x values, which are just their points since it's line segments. We start from the lowest x value, negative 4, to the highest x value, 3. Those are the boundaries of our domain. And then what we're going to do is we're going to plug those into each function, and then we're going to determine the result. So let's take a look. F plus g of negative 4. So let's do f plus g of negative 4. So f of negative 4 is 5. G of negative 4 is 0. So basically it's 5 plus 0 for f of g. So 5 plus 0 is 5. F minus g is 5 minus 0, which is also 5. Next, f of negative 3 is 4. And f of negative 3 is 1. So f plus g is 4 plus 1, which is 5. And f minus g is 4 minus 1, which is 3. Then f of -2 is 3, and g of -2 is 2. So f plus g is 3 plus 2, which is still 5 here. And 3 minus 2 is 1. Then f of -1 is 3, and g of -1 is 2. So we do 3 plus 2 again, which is still 5 for f plus g, and 3 minus 2 is also still 1. Then at 0, f of 0 is 2, g of 0 is 1. So we have 2 plus 1 for f plus g, which is 3, and 2 minus 1 for f minus 3g, which is 1. Then f of 1 and g of 1 are both 1, so we have 1 plus 1 for f plus g, and 1 minus 1, which is 0 for f minus g. And then for 2, f of 2 is -1 because f drifts to low, and g of 2 is +1. So now we have -1 plus 1 equal to 0. Made a quick little error here. That was supposed to be a 2 for f plus g. And then, of course, f minus g is -1 minus +1, which is -2. And then finally, f of 3 is -3, and g of 3 is 0. So f plus g is -3, and f minus g is also -3. Now we're ready to plot our points. For f plus g of x, at -4 we plot 5, at -3 we plot 5, at -2 we plot 5, at -1 we plot 5, at 0 we plot 3, and at 1 we plot 2, at 2 we plot 0, and at 3 we plot -3. There we have it. And then we just use a straight line segment to join our points. Those are all along the same straight line. Then we have a line segment going from there to there, one from here to here, one from here to here, and there we have it. That's the graph of f plus g of x. For f minus g of x, we plot our points again. -4 is 5, and then f of -3 is 3, f of -2 is 1, f of 1 is 1, f of 0 is 1, f of 1 is 0, f of 2 is -2, and f of 3 is -3. So then we join with line segments. These points all have the same slope, so we go there. We go across straight line. These are the segments here have different slopes, so that's what the graph looks like. So this is the graph of f minus g of x, and that is how you identify plus or minus, how you add functions on a graph using graphs. Now let's do a little algebra here. Let's go on to do a little algebra here. So the question says find f plus g, f minus g, fg, and f over g, and determine the domain of each function. Now to do that, what we're going to do is determine the domain of the functions to begin with, because that will save us a lot of work. So the domain of f, since it's a polynomial, there's no domain restriction, so it's -∞ to infinity. And the domain of g, again also a polynomial, is also -∞ to infinity. So we know the domains of the two original functions since they are both polynomials. So let's now do the first question. F plus g of x is simply adding the pieces together. 5 minus x squared plus x squared plus 4x minus 12. We add those together. Negative x squared plus x squared is 0. And then so you'll end up with 4x, and then 5 minus 12 is negative 7. So then the domain, since the original domain was all real number, the domain of the combination will also be all real numbers because we look at where the two regions intersect. And that's that. Let's talk about f minus g of x. Similar type of situation. But remember now we're subtracting the whole expression. F5 minus x squared plus, minus the quantity x squared plus 4x minus 12. In which case we're simply going to subtract. So negative x squared minus x squared is negative 2x squared. And then there's a negative 4x because there's nothing else in the parentheses. And then 5 minus negative 12 is 5 plus 12, which is 17. And as with the addition, the domain of the subtraction is negative infinity to infinity. Again, because we look at where the two regions overlap. Now let's talk about f times g of x. In this case, we're multiplying 5 minus x squared by x squared plus 4x minus 12. And in this case, we're going to distribute. Let's see, negative x squared times x squared is negative x to the 4. Then negative x squared times 4x is negative 4x cubed. Then negative x squared times negative 12 is negative 12x squared, is positive 12x squared. And then this 5 times x squared is another positive 5x squared, so that gives us 17x squared. And then 5 times 4x is 20x, and there's no other x terms. And then finally, 5 times negative 12 is negative 60. So what I've done is multiplied each term in one pair of parentheses by each term in the other. And the domain, again, since it's a multiplication, is where the two regions overlap, which since they're all real numbers, then the domain is all real numbers, negative infinity to infinity. And that's f times g of x. Now let's talk about f over g of x, or f of x divided by g of x. So basically, we're doing 5 minus x squared over x squared plus 4x minus 12. Now, right here, we see we cannot simplify this, but we will factor the denominator because we want to see if there's a domain restriction. And when I can factor the denominator, it turns out we factor the denominator to get x minus 2 and x plus 6, which means that x is not going to be allowed to be negative 6 or 2. So our domain then is all real numbers except for those two values. That means negative infinity to negative 6. We put a parentheses at negative 6. Then we pick up after negative 6, continue to 2, parentheses at 2, pick up after 2, and continue to infinity. And that is the domain of f over g of x. Now let's go over to the other example here. I'd like you to pause the video, try this one on your own, and then check with the work that I've done to see if it's similar, if you get a similar result. Now, first we identify the domain. The domain of f, in this case, is just non-negative real numbers from 0 bracket 0 to infinity. So 0 to infinity, including 0. And g is a polynomial, so its domain is also all real numbers, as was with the previous example. Now, this is actually pretty straightforward. If we do f plus g of x, this is just going to be square root of x plus x minus 5. There's nothing else that we can do. And the domain is where those two regions overlap. The domain would simply be the domain of f, since g is all real numbers. Let's go on to the next part. Part B, f minus g of x is simply square root of x minus the quantity x minus 5, which means we get square root of x minus x plus 5. And that's that. And the domain is also where the two regions overlap, 0 to infinity. Now for part C, f times g of x. And for that, we just do square root of x times the quantity x minus 5. And that's it. No need to distribute. The domain, again, is where the two regions overlap, brackets 0 to infinity. And then for division, we're doing f over g of x. And that is square root of x divided by x minus 5. Now this one, we want to make sure that the domain is clear here. So the domain, let me write it underneath here. The domain is where the two domains overlap, 0 to infinity. But we're going to remove whatever causes the denominator to be 0, which is remove the 5. So that means the domain is 0 up to 5, and then after 5 up to infinity. Make sure you use parentheses at 5. Now let's move on to a few more examples here. I want to make sure we have a good number of examples. So we'll try these two examples and then go on to composition of functions. So we have the domain of f for number 45 is everything except for 2. So negative infinity to 2 and 2 to infinity. And the domain of g is negative infinity to negative 3 and negative 3 to infinity. So let's see if we can do the addition. Subtraction is going to be similar. F plus g of x. That's simply 8x over x minus 2 plus 6 over x plus 3. And of course, we can get common denominator, multiply the numerator of the first fraction, numerator and denominator, by x plus 3, multiply the numerator and denominator of the second fraction by x minus 2, and then the common denominator would be x minus 2, x plus 3. We simplify, combine like terms, we end up with 8x squared plus 24x plus another 6x, that's 30x, and then minus 12. And then the denominator will give us our domain restrictions pretty nicely. Everything except for those numbers. So the domain is everything except negative 3 and 2. There we have it. Subtraction is pretty similar. Just remember that we have to distribute. So f minus g of x is 8x over x minus 2 minus 6 over x plus 3. A little extra work here, which I will kind of bypass for time and space. we get 8x squared plus 24x minus 6x, that would be plus 18x, and then minus negative 12 plus 12. And then the denominator would be x minus 2, x plus 3, and the same domain. So the domain for f plus g would be the same as the domain for f minus g. So I'm just for the sake of space, I'm just going to write that down as the domain for those. Now let's talk about the f times g. F times g of x. F times g of x is 8x over x minus 2 times 6 over x plus 3. And that is pretty straightforward. That's 48x over x minus 2 times x plus 3. And the domain is the same domain once again. So I'm just going to draw a little arrow just for the sake of space. Now for the division. F over g of x. That's just 8x over x minus 2 divided by 6 over x plus 3, which means I would do the reciprocal and multiply. So I'll have 8x over x minus 2 times x plus 3 over 6. And when I combine like terms, I will see that there's actually a common factor between 6 and 8, namely 2. And then when I simplify that, I get 4x x plus 3 over 3 x minus 2. Now the domain has to be exactly the same as before, because we still have to use the domain restrictions, over the intercept, and there was no additional restriction that was introduced. There's no additional number that causes the denominator to be equal to 0. So every combination that we did for this example has the same domain, the very same domain. Let's go on to our next example. Now, first we want to identify our domains. The domain of f is everything to the left, to the right of negative 6, including negative 6. The domain of g is everything to the right of 3, including 3. So bracket 3 to infinity. So then when we look at the intersection of the two functions, we'll see, again, same deal. Let's do a f plus g of x. That's pretty straightforward. It's just the square root of 6 plus x. Sorry, x plus 6. Same thing. Plus square root of x minus 3. We cannot do anything to simplify that. Similarly, f minus g of x gives us square root of x plus 6 minus the square root of x minus 3. Again, cannot simplify that anymore. And then for multiplication, f times g of x it's just the product of what is under the radical, since they are the same index. So we can actually combine them and get square root of x plus 6 times x minus 3. And then finally, for the division, f over g of x is equal to square root of x plus 6 divided by square root of x minus 3. Now, for these first three, the domain is where the two regions overlap. And you can see that the regions start overlapping after 3, because If you look at this region here, it goes from -6 to the right, but this one starts at 3 and goes to the right. So the domain for those first three is just from 3 to the right. That's where the two regions overlap. But for this guy, the domain has an additional restriction. We still look at where the two regions overlap, but we have to now take out whatever causes the denominator to be 0, namely, we have to take out 3. So the new domain is parentheses 3 to infinity. And there you have it. Now, let's talk a little bit about composition of functions. Composition of functions. Now, with composition of functions, we're doing something different from the arithmetic that we did. The four operations we just covered were addition, subtraction, multiplication, and division. Those are called arithmetic operations, and they're binary. That means you do two at a time. Composition of functions means that we're following a chain of commands where the output of one function becomes the input of the next function. So, a composition of function is a function of a function. So the output of one function, which I call the inner function, the output of the inner function is the input of the outer function. Let me show you an indication here. Let's say our inner function is the function g, indicated by this nice little graphic here with gears within. And then the outer function is f. So that's another function with different gears. So we plug x into g. What comes out of g, if we plug x into g, the output is then g of x. That immediately becomes the input of f. And so the output of the combination of the composition is f of g of x. Now, as you can see here, whatever doesn't work in g doesn't work overall. And there are also some things that may work in g, but when the output comes out, they may get stuck in f. That means that x wouldn't work overall either. So when we're doing the domain, we have to bear in mind that whatever works in the composition has to work in the original function to begin with. And the outputs must work in the outer function. The symbol we use for composition is f circle g of x, f of g of x. Think of the circle as like that, meaning off. So f of g of x, the inner function is the one that's closest to the x. So x is the input, then the inner function, then the outer function. And then we can see that there could be a chain of functions from there. So let's take a look at what we at some examples here. We'll go back to our original two functions, f of x equal to 2x squared plus 3, and g of x equal to 4x cubed plus 1. And we want to find f of g of x. Basically, what we're going to do is substitute the inner function into the outer function. So we're going to plug in g of x for f of x. So see, therefore, wherever we see x in the outer function, we're going to plug in the expression for the inner function there. And then we can simplify it. FOIL, combine like terms in this case, and this is f of g of x. It works the other way around as well. G of f of x is, we take g of x and we're going to plug in the quantity for f of x for the variable of g of x. And then we simplify if possible. In this case, we can't simplify, but I want you to realize that in this case, f of g, in general, f of g of x is not the same as g of f of x. They give you two different functions because the order in which you do them does matter. So composition of function is not commutative. We can also do a function f of x. That means we're plugging in a function into itself. It's kind of like cloning itself. So I take f of x and I replace the x's with what f of x stands for again. We're plugging in the function into itself, which we can then simplify. Now, to find the domain of the composition of functions, first you must make sure that the domain of the composition must be the domain of the inner function. And then we can see any additional restrictions. So the domain of f of g of x must be in the region that follows the domain of g. So the domain of g is x is greater than or equal to 1. Then we do f of g of x, which is 1 over square root of x minus 1, and we look for any additional restrictions. In this case, an additional restriction is that x has to be greater than 1, not just greater than or equal to. So the domain overall then is x is greater than 1, or as we may say, x is parentheses 1 to infinity. Now, let's take a look at an example. Or a series of examples. In this question, we have a graph again, and the question is asking for f of g of -1 and g of f of 0 and g of f of -1 and so on. Let's start out with f of g of 0. Sorry, f of g of -1. f of g of -1. What we need to do first is identify g of -1. G of -1, I'll use the green marker here. G of -1 is we look for -1 and we look for the g function. We see that gives us -3. That is the output of g. That becomes the input of f. So now f of -3, we look for -3 and look for the f function. That gives you 1. So overall then the answer is 1. Basically we're saying f of g of -1. First we find out g of -1, which gives me -3, and then I find f of -3, and that gives me 1. All right, let's try another one here. I neglected to put this one down, so I'm going to just write it in. Number 92. We want to do f of g of 1. So let's see again. G of 1 is -5. And then f of -5, sorry, the output of g becomes the input of f. F of -5 is 3. So the result will be 3. So we do f of g of 1 means figure out g of 1, which is -5, and then plug that into f, and we get 3. Piece of cake. Now let's do the others. This time I won't show the preliminary step. I will just go straight at it. G of f of 0. So g of f of 0. So g of f of 0 means find f of 0 first. F of 0 is 2. So we're doing g of 2. And then g of 2 we see is -6. And that's that. As you can see here, f of 0 is what we plug into g. Likewise, that's what we did up here. And we did the same thing here. Now, let's do g of f of -1. So g of f of -1 means we find f of -1 first. We evaluate that. -1, f of -1 is 1. And g of that value, g of 1 is -5. And as you can see, g of f of -1 is different from f of g of -1. Now let's apply that same approach to the following questions. For numbers 11 to 20, find a, b, c, and d, and they have asked us to use the given function that they have here. So let's see if we can do a little work here. All right, so For part A, we want f of g of 4. So let's find g of 4. G of 4 is 3 times 4, which is 12. I'm just going to do a little work on the right side here. So g of 4 is equal to 3 times 4, which is equal to 12. So that means we're finding f of 12. Now f of 12 is simply the square root of 12 plus 1, which is the square root of 13, which we'll leave as that. Part B, g of f of 2. So let's identify f of 2 first. So f of 2 is the square root of 2 plus 1, which is the square root of 3. So g of f of 2 is 3 times the square root of 3. Let's go to part C. And I encourage you to pause the video and try some of these on your own first. Now, we're doing f of 1. F of 1. So let's find f of 1 first. So f of 1 is the square root of 1 plus 1, which is the square root of 2. So basically, f of 1 is the square root of 2 plus 1. And we'll leave it like that because it's a little tedious to try to figure that one out. And then finally, part D, g of 0. Now, we know that g of 0 is 3 times 0, which is 0. So we're then going to do 3 times 0 again, because g of 0 is 0. So the answer is 0. And there you have it. And we have a little computation on the side, which I'll just cordon off in the notes. Now let's move on to the next example here. Now we'll approach this as before. And again, I encourage you to try these on your own before you go through the answers in the video. So we want to do f of g of 4, because that was what was requested right at the top. And as before, we need to figure out what g of 4 is. So g of 4 is 3 times 4 squared plus 2. That gives you 3 over 18, which is 1/6. So basically, we're plugging in 1/6 for g of 4. That becomes f of 1/6, which is the absolute value of 1/6 minus 2, which gives you the absolute value of negative 11 over 6, which is just positive 11 over 6, and that's that. There we go. Part B, g of f of 2. So now we're going to find f of 2. So it turns out that f of 2 is just absolute value of 2 minus 2, which is 0. So g of f of 2 means we're going to plug in 0 for x in the g function, 3 over 0 squared plus 2, which is 3/2. Then for part C, we're doing f of 1. And again, f of 1 is just 1 because we do absolute value of 1 minus 2, which is the absolute value of negative 1, which is 1. And then we plug that into the function. So again, absolute value of 1 minus 2, which is same as before, 1. And then finally, for part D, we do g of 0. Now, g of 0 is 3/2. So now we have to find 3 divided by the square of 3 over 2, and then we're going to add that to 2, simplify. You can do that on your calculator. And that will give you 12 over 17, which you can get by multiplying numerator and denominator by 4. So 4 times 3 is 12. 9 over 4 times 4 is 9. 2 times 4 is 8. 8 plus 9 is 17. And there you go. Of course, you need to make sure you work systematically through these, because the only way to get good at this, it's by practice. Lots and lots of practice. Let's push on to the next examples. So now for this set of questions, it's a little bit more tedious. Question says, find the functions and state their domains. So what I'm going to do is right off the bat, I'm going to state the domains of the function on the side. So the domain of f, since it's a polynomial, is all real numbers. And the domain of g is also all real numbers, also because polynomial, which means the compositions will also have no restrictions. So the domains will all be negative infinity to infinity. So this one is just basically finding the composition. F of g of x really means f with g of x substituting in for x. Just like our example. So I do 2x squared plus 3 squared plus 1, because I plug g into f. And then I can simply distribute. Remember, you have to do 2x squared plus 3 times itself. And then when you work that out, you get 4x to the 4 plus 12x squared plus 9 plus that 1, which gives you 10. And part B, g of f of x is a substitution the other way around. So we're doing g of f of x. So in this case, we're doing 2 times the quantity x squared plus 1, and that quantity squared plus 3. And if you do a little distribution here, you'll get 2 times x squared, x to the 4 plus 2x squared plus 1. And then we're going to add 3, so that overall will be 2x to the 4 plus 4x squared plus 2 plus 3 is 5. And then for part C, f of x is equal to f with f of x plugged in. So it's just x squared plus 1 squared plus 1. Of course, that's x to the 4 plus 2x squared plus 1 plus an extra 1. And that gives you plus 2. And then finally, part D, g of x. which means we're plugging g into itself. That gives us 2 times the quantity, 2x squared plus 3 squared, then plus 3. We're substituting g into itself, so we do 2 times 4x squared plus 2 times 3 is 6, and then double that is 12x squared plus 9, and then plus 3. And if you distribute that and combine like terms, you get 8x, so this is supposed to be a 4. 8x to the 4 plus 24x squared plus 18 plus 3 is plus 21. And then domain of each composition is all real numbers simply because the original domains were all real numbers, so there is no domain restriction in the composition. Last set of examples, and then that will be it for our lesson. So for number 38 here listed, I put it over on the side because of space issues. So what I will do is first we'll list our domains on the right side, and then we can talk about the compositions afterwards. So the domain of f is everything except for -3. Negative infinity to -3 union -3 to infinity. Parentheses everywhere. And the domain of g is everything except for 0. Negative infinity to 0 union 0 to infinity. So let's start off f of g of x. And that is f of x being plugged, g of x being plugged into f of x. So wherever I see x in the f of x function, I'm going to put 2 over x. And that I simplify by multiplying numerator and denominator by the common denominator, which is x. And that gives me 2 over 2 plus 3x. Now, what is the domain of this? We note here that this part only works if x is not equal to -2/3. But we also know that the domain of the inner function is the only part we can look at. So we have to also look, the domain of the composition is the domain of g minus -2/3. So since g did not include 0, that means it's from negative infinity to -2/3, and then from -2/3 to 0, and then from 0 to infinity. In other words, we had to take out an additional -2/3 from the domain of the inner function, because we have to keep the domain of the inner function for the whole thing to work, but we have to take out whatever else caused a problem in the composition. Part B will be similar. So we're doing g of f of x. In this case, we're plugging f into g. So we're talking about 2 over, let me write it this way, 2 divided by the quantity x over x plus 3. Which means 2 times x plus 3 over x, which means 2x plus 6 over x, We only multiply the numerator by a fraction, by a whole number. Now, again, please note that in this case, x cannot be 0. So the domain here of g of f is the domain of the inner function minus the additional restriction of 0. So where that means we're going from negative infinity to negative 3 union negative 3 to 0, because we have to throw down the 0, union 0 to infinity. Now let's talk about part C, f of x. So basically, we're replacing all our x's with x over x plus 3. Makes it a little bit tedious. We multiply the numerator and denominator by the common denominator, which is x plus 3, which I'll put in parentheses, of course. And what that will do is cancel the x plus 3 from the top, leaving just x. Cancel the x plus 3 from here, leaving just x, and then 3x plus 3. And so the bottom will work out to be x plus 3x plus 9, which is 4x plus 9. So with this one here, x cannot be negative 9 over 4. So then the domain of f is equal to the domain of f, taking out negative 9 over 4. So that is negative infinity to negative 3. Negative 9 over 4 is negative 2 1/4, so it's to the right of negative 3. Union negative 3 to negative 9 over 4. Union negative 9 over 4 to infinity. And then finally, part D, which is g of x, which of course means 2 divided by 2 over x, which gives you 2 times 2 over x, which is 2 times x over 2. Which is x. Now there's no domain restriction on this particular thing, but we still have to use the same domain of the original function. So the domain of g is equal to the domain of g, and we have nothing to remove from that, so it's just negative infinity to 0 union 0 to infinity. There we have it. And that's all for this lesson for today. As always, I strongly recommend that you make use of Khan Academy and your textbook. And as always, I recommend that you visit OpenStax and try some of the questions from their free textbook app. OpenStax.org is the website. OpenStax, OPENSTAX. You can also find the app on Android. I do not know if it's on iPhone. But as always, review, practice, memorize, and practice some more. All the best.